Hello, this is Divigati Math, and well, in this video we're gonna prove this inequality: n to the nth power plus n in parentheses to the nth power is larger than or equal to the 2n factorial. So we'll prove this for all positive integers and for all natural numbers and well, I proved this in two ways, and in this video I'm gonna show you the first way. So let's move on to the proof then. Alright, so first applying the arithmetic mean, geometric mean inequality, we have, so the arithmetic mean is larger than or equal to the geometric mean, and we apply the arithmetic mean, geometric mean inequality to the two numbers n to the nth and n. So n to the nth power plus n is larger than or equal to 2 times the square root of n to the nth times n. And so n to the nth times n is simply n to the power of n plus 1, and then you take the square root. So that is n to the power of n plus 1 over 2. So n to the nth power plus n is larger than or equal to 2 times n to the power of n plus 1 over 2. So this is just straightforward from the arithmetic mean, geometric mean inequality. We apply the arithmetic mean, geometric mean inequality to the two numbers n to the nth power and n. And then while raising both sides to nth power, we have this: n to the nth power plus n in parentheses to the nth power is larger than or equal to 2 to the nth power times n to the power of n times n plus 1 over 2. So this is just raising both sides to the nth power. And well, n is a positive number, so raising both sides to the nth power and the inequality sign doesn't change. It stays the same. It only changes when n is a negative number. Then raising both sides to the nth power, we change the inequality sign, but in this case n is positive, so we don't need to change the inequality sign. And well, note that the n times n plus 1 over 2, the power of n here, n times n plus 1 over 2, is equal to 1 plus 2 plus 3 plus all the way to n. So n times n plus 1 over 2 is simply the sum of the first n numbers. The first n positive integers, first n natural numbers. And so using this formula, we have here 2 to the nth power times n to the power of n times n plus 1 over 2 is equal to 2 to the nth power times n to the power of 1 plus 2 plus 3 all the way up to n. And well, n to the power of 1 plus 2 plus 3 all the way up to n is simply n to the first power times n to the second power times n to the third power all the way up to n to the nth power. So this thing right here is equal to 2 to the nth power times n to the first power times n to the second power times n to the third power all the way up to n to the nth power. And this can be expressed as a product. This is equal to the product from k equals 1 to n of 2 times n to the kth power. Well, you can see here that we have n to the first times n to the second times n to the third all the way up to n to the nth. So that's why we have n to the k from k equals 1 to n. And before it, in front of it, we have 2 to the nth power. So basically we're multiplying 2 n times. So that's why we have the factor 2 here. Multiplying n times because k from k equals 1 to n. So multiplying n times. So we have 2 to the nth power. And so, well, so basically this shows that this is equal to this product. And we already showed that this thing is larger than or equal to this thing, and where this thing is equal to this thing. So we have this inequality right here. Alright, so we have n to the nth power plus n in parentheses to the nth power is larger than or equal to the product from k equals 1 to n of 2 times n to the kth power. So this is one of the main inequality that we will use to prove the final inequality. The n to the nth power plus n in parentheses to the nth power is larger than or equal to 2n factorial. This is one of the main inequality that we will use to prove that. So remember it or note it down or something, because this is gonna get messy. Well, moving on to the next slide. Where is it? Alright, so well, next, note that the 2n factorial can be expressed as a sum, not a sum, as a product from k equals 1 to n. So 2n factorial is equal to the product from k equals 1 to n of 2k times 2k minus 1. Okay, why? Because first, plug in the k equals 1, we have 2 times 1. And then k equals 2, we have 4 times 3. K equals 3, we have 6 times 5. And so on. Up to k equals n, is we have 2n times 2n minus 1. So that's just 1 times 2 times 3 times 4 times 5 times 6 all the way up to times 2n minus 1 times 2n. And that is 2n factorial. So 2n factorial is equal to the product from k equals 1 to n of 2k times 2k minus 1. Alright. So, well, this is just a reminder that this is the inequality that we are solving, we are proving. And well, so to prove this inequality, we need to prove this inequality right here. Why? Because we showed that, so first, I'm gonna erase all this so that it doesn't get too messy. So we showed that this thing right here is larger than or equal to this product. And now, if we can show that this product is larger than or equal to this product, which is 2n factorial, then by the transitivity rule of inequality, we have this thing right here that I'm circling is larger than or equal to this thing, which is 2n factorial. So it's just transitivity rule of inequality. So, well, oops. So now our goal for now is to prove this inequality involving two products. And well, so we can prove that each term of the inequality, each term of the products on the left hand side and the right hand side, well, we can prove that each term on the left hand side is larger than or equal to each term on the right hand side. And we just take the product, and the product of the left hand side, the product of the terms on the left hand side will be larger than or equal to the product of the terms on the right hand side. Well, we can do that, we can prove it like that, but unfortunately that way of proof doesn't work for n equals 2. So, well, we just check by hand that the inequality here is true for n equals 1 and n equals 2. And then we will prove this inequality for all n larger than or equal to 3. So just plug in n equals 2 and n equals 1 and check that this inequality holds. And then we will prove this inequality for n larger than or equal to 3. So we will prove that each term of the product on the left hand side is larger than each term of the product on the right hand side. And to do that, well, we simply prove 2 times n to the kth power is larger than or equal to 2k times 2k minus 1. And well, we can divide both sides by 2, and all we need to prove is this. So n to the kth power is larger than or equal to k times 2k minus 1. This is what we need to prove for n larger than or equal to 3. Alright, and then after we multiply it out and just rearrange it algebraically, then we get, well, k times 2k minus 1 is 2k squared minus k, and well, just move it to the other side. we get this inequality. So this is not what we proved, this is what we need to prove. So we need to prove that n to the kth power minus 2k squared plus k is larger than or equal to 0. This is what we need to prove. And well, so we need to prove this inequality for n larger than or equal to 3 with the condition that k is between 1 and n, because we will only take the product from k equals 1 to n, so k needs to be larger than or equal to 1 and less than or equal to n, so between 1 and n. And well, of course n is always larger than or equal to k from this condition, but if we say that n is larger than or equal to k for k equals 1 and k equals 2, that would include the case when n is 1 or n is 2. And well, we're proving this for n larger than or equal to 3 only. So we want to just use the condition n larger than or equal to k for k larger than or equal to 3 only, so that we only deal with the cases where n is larger than or equal to 3. We don't want to deal with the case n equals to 1 and n equals to 2 here. We already checked that this inequality holds for n equals 1 and n equals 2, and we're just proving for n larger than or equal to 3. And so, well, again, just check that this inequality is true for k equals 1 and k equals 2. By hand, just plug in k equals 1 and k equals 2 and check that this inequality is true for n larger than or equal to 3. Alright, so just check by hand the cases when k equals 1 and k equals 2, and for k larger than or equal to 3, we will use the condition that n is larger than or equal to k. Now finally, we're using this condition because when k is larger than or equal to 3, n larger than or equal to k means n is larger than or equal to 3, which is the case that not the case, but which are the cases that we're dealing with. We don't want to use the condition n larger than or equal to k when k is 1 or 2, because that would include the case when n is equal to 1 and n is equal to 2, and we don't want to deal with those cases here. So for k larger than or equal to 3, we will use the condition that n is larger than or equal to k, and then we have this inequality right here. So well, n is larger than or equal to k, so n to the kth power is larger than or equal to k to the kth power. And so we have n to the kth power minus 2k squared plus k is larger than or equal to k to the kth power minus 2k squared plus k. Alright, and k, well, k is larger than or equal to 3, so k to the kth power is larger than or equal to k to the third power. And so we have this thing is larger than or equal to this thing, k to the third power minus 2k squared plus k. So k to the kth power minus 2k squared plus k is larger than or equal to k to the third power minus 2k squared plus k. Alright, and well, here we're going to use a bit of calculus. And well, let the function f of x be equal to x cubed minus 2x squared plus x, and its derivative f prime of x is equal to 3x squared minus 4x plus 1, and this derivative is larger than 0 for, I'm gonna go to the next slide here. So that derivative is larger than or equal to, that derivative is larger than 0 for x larger than 1. You can check that. It's just solving a quadratic polynomial and find where it's positive or negative. So the derivative of the function f of x is equal to x cubed minus 2x squared plus x. The derivative of that function is larger than 0 for x larger than 1. So the function f of x is increasing on the interval 1 to infinity, on the open interval 1 to infinity. So for k larger than or equal, so well, the function is increasing. So for any k larger than or equal to 3, f of k is larger than or equal to f of 3. So well, here is f of k, and it's larger than or equal to f of 3, and just plug in x equals 3, and you can check that f of 3 is larger than 0. So, well, so we have for any k larger than or equal to 3, we have k to the third power minus 2k squared plus k is larger than 0. So, well, here, and using this inequality that we just proved here using the function f of x, and well, let me go back to the last slide for a moment. So, well, and we proved that this thing is larger than or equal to this thing, and this, and then it's larger than or equal to this thing, and this thing is larger than 0. So that means, well, first off, we prove that this is larger than 0, and when it's larger than 0, we can also say that it's larger than or equal to 0, and it's still true, because larger than is like stricter, or more strict, I don't know which word, but stricter than larger than or equal. So when it's larger than 0, we can also say that it's larger than or equal to 0, and it's still true. And well, so from the using the transitivity rule of inequality, we showed that this is larger than or equal to 0, which is exactly what we wanted to prove here. And so we proved this for k larger than or equal to 3 and n larger than or equal to 3. And well, we checked that inequality by hand for k, we checked that inequality for the cases when k is equal to 1 and k is equal to 2. And so this inequality that I'm circling here is true for any k between 1 and n, and for n larger than or equal to 3. So we proved that inequality. Alright, so basically we proved this inequality for any k between 1 and n, and for n larger than or equal to 3. And now we're multiplying both sides of this inequality by 2, and then taking the product from k equals 1 to k equals n of both sides, we obtain this inequality, which is what we wanted to prove. And we obtained this inequality for n larger than or equal to 3. And we checked this inequality for n equals 1 and n equals 2. So this inequality holds for all positive integer n. And recall that the right hand side, the product on the right hand side here is simply 2n factorial. So, well, using this inequality and using, let me go back to the first slide, and using this inequality right here, alright, and well, using the transitivity rule of the inequalities, finally we get this inequality for all positive integer n. So well, it was quite messy, but actually this is not my favorite proof, and I proved it in another way, and in the next video I will show you the second proof of this inequality. So well, thanks for watching.